Hello and welcome to another episode of the Oxford Online Maths Club. Nothing happens just now, don't look at chat. We're back for another episode. I'm joined today by one of my students, Aditi, who has agreed to talk to you about some math, which is brilliant. Say hello.
Hello.
Cool. There we go, and we've got our sound working and everything like that. Hi to everyone in chat. If you're new on the live stream, you can join this live chat by going to slido.com slash OOMC. It's a little bit like YouTube live chat, except it has replies and it has thumbs ups and things, so you can talk to other people about what's going on the live stream, talk to other people about maths, talk to other people about how their day was, stuff like that. We're joined by Aditi live on stream, and Christian is in chat to help answer questions as they come up. I'm keeping one eye on chat as well. If you see me look in this direction, because I'm looking at what you're saying in chat. It's below me in virtual space, but it's over there in the real world. Right. So this is the Maths Club that we've been running on the Oxford Maths website at maths.ox.ac.uk/r/club. I want to say thank you to Matt Parker below, who's reminded me to mention the further reading. And mention the fact that you can set your name to be anything in the Slido chat. You can join in. Set that to whatever you want to. An anonymous person, so you can also be anonymous as well as being Matt Parker, would like to know what year you're in. Aditi.
I'm first year. I'm first year at New College. Yeah, doing maths.
It's been a strange first year.
Yeah.
So hopefully by the time we get to second year, we can give you a more normal year of what's going on. And Myers asked the default question, which is, I should have warned you about, which is, what A-levels did you do when you were doing A-levels?
Right, I did maths, further maths, and physics. I only did 3, which is okay, I guess. I did do computing in year 12, but I did drop it in after year 12, so I did only do 3. Well, I didn't do them, I guess.
This backs up something I've been saying a few times on open days and things, that 3 A-levels is really okay for us. Maths, further maths, and then we ask for a third one, but maths and further maths are the A-levels we care about most. Hannah says that they have been anonymous since week 1, which was about 16 episodes ago. But they're now Hannah. So hi, Hannah. Okay, get a shout out. Right, okay. Josh has got the terrible suggestion that you could set your name to be my name and then answer all the maths questions incorrectly. Josh doesn't know that I've already cornered the market on answering maths questions incorrectly with my name, so no need for anybody else to join in with that. Right, okay. I think that's enough waffle at the start, and we've checked that the microphones are now switched on, so professional live stream. That's nice. I think you can switch between, people are now talking about being anonymous, you can switch between being anonymous and not anonymous. And I think someone once said, and this was adorable, they said that they switched to anonymous when they were not confident, and they switched back to being them when they were doing a sort of meme that they wanted appreciation for. Right. Christian says Slido won't let Christian log in. We're having all the issues. I'm going to hand over to you to introduce what maths you're doing, and I'm going to get Christian into the Slido. Cool. Right. Let's put slides on the screen. Fundamental Theorem of Calculus with Aditi at New College. Over to you. What are we doing today?
Yeah, so as the slides say, the plan is to actually prove the fundamental theorem of calculus in a somewhat rigorous way. So as I'm sure you know, that the fundamental theorem of calculus links differentiation and integration. So first we'll try to actually define what they are, because also somewhat rigorously. So yeah, we will need a series of proofs to get to the fundamental theorem of calculus. So hopefully we'll learn some other things as well on the way. Okay. So let's move. Okay, so firstly, obviously fundamental theorem of calculus is about functions. So it would be good to define what a function actually means. And it's actually a lot more vague than you think, because in school we're normally used to functions being nice and polynomials and exponentials, but function really is just way more general. It's just any kind of way to assign a value to every point in an interval or on a set. So it doesn't have to be in the whole of real numbers. We're just assigning one value to each x on our set. So that's what a function is. So you can have some weird functions. I can try and write something. So you can have some weird functions. You can kind of have them. You can have. Let me try and draw something. So you can have something like this, kind of broken apart, or you can have something smooth and nice, like we're used to quadratics. So these are both functions. But then there are various properties of functions that we can talk about. So continuity is actually the niceness of a function. So the functions that we've seen in school are mostly continuous. So continuity generally just means that you can draw the function with a line with a pencil without taking the pencil off the paper. That's what this means. But to properly define it, we need the idea of limits. So this is a limit. And I think they may have seen limits before.
Maybe not written like this with the limit. I suppose I should say that we're keeping all the kind of scary university notation in here, just because some people like to see the scary university notation. But we're going to try and explain. I liked what you said about drawing it without taking your pen off the page. So yeah. That thing lim x goes to a means as x gets really close to a, which is something we say quite a lot in kind of calculus or if you think about the way differentiation is like tangents and tangents and chords on graphs, that idea about making x get really close to a comes up quite a lot. So it's just a little bit of notation. We thought about taking out all of the scary notation, but it's not quite the same without the scary notation.
Cool. It's very hard to. Okay, so what is this exactly saying? This is saying that, so for example, if you look at this function, then as we approach, say, this point, let's just name it a. So as we approach this point, maybe from the left, the value of this function kind of approaches this point, this value. So, and maybe f of a is defined to be this value. So it's not continuous because the function values don't actually tend to f of a. There's kind of a gap. And then if you look at it from the left, from the right, then it does seem like the function values tend to the value of f of a. So it's not continuous overall because the left limit and the right limits aren't the same. So this is what we mean. So we need to introduce the idea of left and right limits as well. So yeah, if we look at a continuous function, then as we move towards a from the left, the function goes to some negative value here. And then it's the same negative value if you move to it from the right. And if this is true for all values on which the function is defined, then the function itself is continuous. So this is what continuity means. And then differentiability, which is, I think they're both in some sense measuring how smooth the function is. But anyway, so derivative of a function is this limit, if it exists. And if the limit exists, then the function is differentiable. And this is another limit, so it's treated like a limit. So this, I think maybe in school we kind of, this is slightly different to what we see. I think first principles is something like limit as h approaches 0 of f of x plus h minus f of x over h. This is what we see in school, maybe. But these are equivalent because here we're basically saying that your x plus your x plus h is your x. It's strange notation, but maybe I should have named this limit as h approaches 0 of f of a plus h minus f of a over h. So yeah, so this is basically just replacing a plus h with x. And then as h goes to 0, x plus h goes to a. So these are equivalent definitions. So this is just if this limit exists, then the function at a is differentiable.
Maya's got a good point. Sorry, just to interrupt. Sorry, with chat. Maya's got a good point in chat about what does it mean. Well, so it's a question. What does it mean for the limit to exist? I guess normally when we do maths, we don't say, "Oh, that's 2 plus 2 is 4" if 4 exists. Whereas here we're sort of defining a thing as saying, "Oh, if that thing exists." I guess we've got some examples coming up of what it would mean to not exist.
Yeah, there are many ways in which limits cannot exist. So this was an example in which the limit does not exist, because if you go from the left and if you go from the right, you kind of end up at different values, and that means it's kind of a contradiction. So the limit doesn't exist. Also, it can just diverge. If it goes off to infinity, then it doesn't technically exist.
I guess you only say that the limit exists if no matter how you get close to the point A, this thing is always the same number. So that limit as x arrow A is supposed to include all of the different possible ways that x might get close to A. And in the picture, there's sort of you get different answers if you go from the left or from the right. So I guess we're saying it doesn't exist, like not independent of how you approach it. Hannah in chat has got in with the Mean Girls reference. We all knew the Mean Girls reference was coming. And look, Hannah, if you set your display name as Hannah, then I can call you Hannah in chat. Right, anyway. And Billy wants to know if that's more of a philosophical question about what does it mean to not exist, which maybe it is. But here it's sort of part of the definition. Do you want to talk about differentiable? Oh, sorry. I've interrupted you just before you got to the kind of punchline of the slide. Sorry.
No, it's fine. Okay, so the function itself is then differentiable if it's kind of differentiable on every point on which it's defined. So the function, if it's not differentiable on even one point, then it's not differentiable. Okay, so let's move on to some examples. Shall I go? Next slide?
Yeah, let's go. Let's do some examples. We're going to do a Slido poll as well. This is very high tech. So we've got a picture. We've got a picture, and the question is this function continuous? Draw it with a pencil. And is it differentiable at all points?
Yeah.
Can you give it a number for its derivative? Slido poll.
So this function is only defined between -4 and 4, which is fine. You can kind of restrict the bounds on which a function is defined. So we only care about -4 and 4. So we're checking for, is it continuous? And is it differentiable?
I'll try to zoom that so it fits on the live stream. Oh, people are voting. Off they go. Look at them go. Currently, it's like commentating a race. Currently, votes for all options.
Wow.
People, I think consensus is for the first two options are popular. People think this is continuous. Maybe we'll reveal that, in fact, this function is continuous. So away from 0, it's fine, right? It's quite nice away from 0. It's just obviously well behaved and everything's lovely.
Yeah.
At 0, you might get a little bit scared, I guess, because the function's quite spiky. But it is still continuous because it doesn't matter how you come in, how you get close to 0. If you come in from the left or the right, or some other way, looking at left and right values, it gets really small on both sides. It gets really close to 0 on both sides.
Yeah. So we think it is continuous, right? We think it is continuous because you can kind of draw the function without taking your pen off the paper, and it's without having to list it or anything. But is it differentiable?
Chat currently is voting for not differentiable.
Not differentiable. Interesting.
I guess, and there's people watching the live stream not in chat can't see the kind of chat underneath the poll, so I'll read some stuff out. People are saying that you can't differentiate at 0. Yeah, people are agreeing that it's 0.
Yeah, and then we can again kind of think about that by left and right limits, because if you kind of go from the left to 0, then the gradient is -1, but then if you go from the right, the gradient is +1. So it can't quite be differentiable at 0 if the gradient tends to different things.
Yeah, So I suppose
That's the right idea.
It's almost a differentiable function. Like away from 0, on the right hand bit, that's fine. It's got a nice sensible derivative 1. On the left, nice sensible derivative -1. At 0, its derivative is sort of neither 1 nor -1. And as you come in close to x, it's not true. Maybe you could think of it like this: it's not true that the chords, if you join 2 points on the curve, if you join 0 to a different point on the curve, the chords don't all get closer to the same tangent. I guess there's sort of not a unique definition of what the tangent should be at that point there. Okay.
Yeah, and then I guess if we put the extra condition that x is not equal to 0, so we kind of just define this function on, all the points from -4 to 4, but x is not 0, then this function is differentiable and continuous, like James said.
Yeah, and George's one in chat. George has asked if we could say it's differentiable except when x is 0, and I'm fine with that as something that we could say. Yeah, differentiable when x is not 0, or if you just take away the point 0. The way Maximus, I agree. We don't have a gradient we don't really have a well-defined gradient at 0, do we? It's too spiky. It kind of sort of feels a bit like it should be 0, but that's not really how these things work. I like symmetry or something, but okay, never mind. Right. No, it doesn't have a well-defined gradient. Good, right, okay. Chat did really well on that one. That was continuous but not differentiable. Let's have another one.
Let's have a slightly more interesting function. Let's go for sine of 1 over x.
Have I put this on the curve sketching, on the further reading at some point? I can't remember. Well, we might have done it on a special curve sketching episode. I sort of wish, if we didn't have the picture, that could be curve sketching exercise. Sine of 1 over x. Sine of 1 over x is really horrible.
Yeah, so I mean, obviously, interesting things happen when when x goes near 0, and it's not defined for x equals 0. So we kind of just define this function to take 0 to 0. So we do actually define the function on the interval -1 to 1, the whole interval. So we can think about if it's continuous or not.
Raphael says that we have done this one in curve sketching homework on the further reading. If you've just heard about further reading for the first time, then you might be interested in a sort of series of posts on the Oxford Maths Club website. I'm trying to talk to the camera. The Oxford Maths Club website has other related material for each of the live stream episodes for you to read more about. It's posted on Friday, so check back on the weekend for more mathematics. This live stream was sponsored by the further reading, which doesn't make any sense. Doesn't make any sense at all. Yeah, so sine 1 over x. Josh says that we've ruined sine. It's going to get worse. Sorry, Josh. This 1 over x thing. People are quite happy with it, though. In chat, people are all voting for continuous and differentiable.
Right, nice.
What a lovely looking graph, an anonymous person says in chat. I don't know how we're going to break it. How are we going to break it to chat?
Okay, so let's think about maybe not x equals 0. If we don't think about x equals 0, then it seems okay. If you think about any particular point, then it feels continuous at that point, and it feels differentiable.
Yeah, I guess it's quite wobbly away from 0, but if you're interested in a particular point, like 1/3, then you could zoom in near 1/3. If we're just dealing with limits is what happens when you get really close. We could just look really near 1/3, and then it'd be kind of all right.
Yeah, and then you can do this zooming thing for any point, literally any point that is not 0. But okay, so I guess x equals 0 is something to focus on. So is it continuous? So what does the chat think again?
So chat at the moment is very much in favour of continuous and differentiable.
Continuous.
I think people. So behind this poll on the live stream, people in chat are talking about what's going on at 0, because Maya says it's all smooth, and it is kind of all smooth, except maybe there could be something weird going on at 0. And an anonymous person is unhappy about this function where it feels a little bit like cheating. Someone says, to have one definition when x is not 0, and then just throw in a number when x is 0.
Yeah, I mean, functions are generally very, very general, so generally very general. Well,
generally very general.
You kind of just define, you just have to basically tell where does each particular point go. So it's
Yeah.
fine to have conditions which are broken.
I think we got away with something earlier. Like a couple of slides ago, we said a function is something that takes a value. It has exactly one value for each x, and that's it. And
That's it.
nobody found that weird or spooky. And now somehow a few slides later, we've got this where, hey, it's got a value for all x. You didn't say I had to write it neatly in one line or just use known expressions. I'm allowed to have weird stuff like this. So somehow that definition of function included lots of weird stuff like this.
Yeah.
People are trying to talk about asymptotes, so I've got to try and remember A-level mathematics to remember what an asymptote is. Matt Parker in chat knows the chain rule, so Matt Parker knows the chain rule and has had a go at using the chain rule, and is worried about zero. People are now starting to be more worried about zero, I think.
Yeah, that's in general a good strategy. Because
do you want to hit them with what's going on at zero?
Yeah, okay, so we can discuss about what's going at zero. So first, I guess we should think about continuity. Okay, so this graph is continuous if the limit as x approaches zero of f of x is f of zero, which is zero. Right. But as you get closer and closer to zero, we keep having this function take values -1 and 1. So it can't possibly go to zero. Because however close you are to zero, you can always have an x value such that the value of the function is 1 and the next value such that the value of the function is -1. So it does not approach zero. This is kind of the symbol that we use. It does not go to zero, so it's not continuous. So it's not continuous.
Is that a crossed out arrow? I've not seen that.
Because we say something like f of x goes to zero, and if it doesn't, you just cross it out.
This is bad news for democracy, by the way, because we did a vote and most people voted for continuous and differentiable, and bad news, 37 people who voted for continuous and differentiable. The function is not continuous. To be continuous at zero, it would have to be however you got close to zero, it's got to go towards the same value. Whereas here, if you come in along the top along those bunched up top of those oscillations, if you read along the top, then it looks like it's going to have to be the value 1 as you get close to zero. But if you look at the bottom of the oscillations, more and more oscillations, if you read along those, it looks a bit like the value is going to have to be -1 as you come in along there. So it's not the case that however you come in towards the origin, you get closer to the same value. Here, the way you come in towards the origin really matters. It kind of looks a bit like, if you just look at some points along the top, it looks like it's going to go to 1. If you come in at the bottom, -1. And 7 people below have voted for, I guess I should add things together. So like 9 people think this is not continuous, and they're right. This is not a continuous function. Weird. It's kind of like the point at zero. It's kind of, we've thrown it in as f of 0 equals 0, but that hasn't really fixed it continuity wise. It hasn't made it continuous.
Yeah, exactly.
Yeah, limit at 0 is not defined.
Yeah. So is it differentiable? Is the other question. So it's differentiable. Again, we can go back to the limits. So if it's differentiable, if the limit as x approaches 0 of f of x, which is sine of 1 over x, minus f of 0, which is 0, I guess, over x minus 0 exists.
And that's really bad, right?
Yeah, it's. I mean, you've got weird things happening in Sine, and if you're dividing by x, so it feels like it's not differentiable.
So 1 over x would have like a vertical asymptote at 0, so definitely not some nice value. Sine 1 over x, I think that's even worse at 0, which is really, really nasty. Doesn't have a good value at 0. I guess, if this was differentiable, if it was going to be differentiable, then it would have to have a derivative at 0. I don't really know what that derivative... Last time I kind of felt like I had an idea about what the derivative should be. It didn't have a derivative at 0. This one doesn't have a derivative, and I'm not really sure what I would want it to be. Because a derivative would be like if it was like a nice smooth bit of straight line. But it's horrible. It's not differentiable either. Chat in shambles. Okay, right. This is a horrible function. It's horrible. I kind of want it to go away. It's not continuous, and it's not differentiable. 0 lets the team down. The rest of the function is all actually quite nice. It's just at 0, there's so many oscillations as we come in towards it that it can't make its mind up about what value it's going to, about what its derivative should be. There's no sort of consensus as it comes in what the value or derivative should be. Ugh. Okay.
Okay. So let's make things a little bit more complicated.
Sure. Let's hit them with another one. What is this? So this is x times sine 1 over x. It's the same thing as before, but you've multiplied it by x.
Yep. And you kind of see that this is going to be a useful thing when determining if it's continuous and differentiable, that this graph is kind of always between the lines y equals x and y equals minus x. It's kind of bounded by these lines. It's terrible drawing. It's bounded by these lines.
Oh, yeah, so it kind of looks like like an X that's been coloured in more and more. Yep. There are infinitely many oscillations. I love seeing the early votes come in. So later on, I think people's votes are kind of influenced by what people previously voted for. Early on, ooh, ooh. So people are not happy. Well, I don't know. I think I'm trying to characterise how people felt about the previous function. It was horrible. It was nasty. This one, it's kind of got that kind of funneling shape going on. I've got a kind of good feeling about its values. I'm scared of how much it oscillates as you come in. Maybe we should have got them to sketch sine 1 over x, because it's not obvious what that looks like. It's got lots of oscillations. As 1 over x gets really big, it goes through 360, 720, the next multiple of 360, faster and faster and faster, and it goes through infinitely many. Yeah, so someone's pointed out, we've tried to squash it by multiplying it by x. It's got kind of squashed into this funnel shape, but the infinitely many oscillations are still there. It's now behave, but in a smaller blob.
Yeah, now they're bounded by these lines. Which may or may not help the differentiability. It may change the differentiability and continuity conditions. So what does the chat think?
Chat at the moment is voting for, it's pretty close. So I guess winning at the moment is continuous but not differentiable. And I think overall continuous has more votes than differentiable if I do some quick adding. It's like 2 to 1. Is this one continuous?
I think it is. It is continuous, yes.
Results. Okay.
Which is kind of crazy that it is continuous, because a few slides ago we defined continuity as kind of being able to draw this function without lifting your pen off the paper. But I don't think I can draw this function without lifting my pen off the paper. It's very hard to, especially at 0. I mean, you can't do it. I think
I can, but only because I've got pretty low standards of what my drawings look like. So it's very wiggly there. So I'll just colour that bit in. Which looks like what Desmos has done, to be honest. Pictures from Desmos, right? Just colour that bit in. It's very wiggly. But this one is continuous at 0. Yeah. It's continuous because...
Let's try and...
Yeah, sorry.
Okay. So we can actually go back to limit definitions and try to prove this. So the limit definition of continuity is that the limit as x approaches 0 of f of x is f of 0, which is defined to be 0. So if this does turn out to be the case, then it is continuous. Okay, so limit as x approaches 0. Now f of x is x sine of 1 over x. And now this is where the fact that it's bounded by these lines comes into play, and the property of the sine function. So sine of x is always bounded between 1 and -1. So that means this thing inside the absolute value sign is always less than x. Right? So as x goes to 0, mod x goes to 0, so this entire thing goes to 0. So it is continuous.
Thank you, Maya.
Hopefully that's convincing.
Yeah, so I guess the way I would say it, I am always nervous about all these limit notations. The reason I think it's continuous is that if you move x closer and closer towards 0, then it doesn't really matter where you precisely put x. The values there are definitely getting smaller and smaller. They have to, because, well, yeah, as you said, sine's between 1 and -1, and it's being multiplied by x.
Yeah, exactly. The value of the function is approaching the value of the function at 0, which is defined to be 0.
So here the values are kind of nicely behaved as x goes towards 0. I should say I'm saying well behaved quite a lot for a function. If it's continuous, it gets marks for being well behaved. If it's differentiable, yeah, that's pretty good. You get to be called a little bit well behaved. Do we think it's differentiable or not? Let's have a quick look at the poll. Votes are massively in favour of it not being differentiable by like 3 to 1.
Yeah.
And it's not, right?
It's not differentiable. It's very good intuition. So it's not differentiable. And I guess James is not going to like it, but I'm going to revert back to limits and trying to prove it by using limits. Okay, so if it's differentiable, then we want the limit as x approaches 0 of f of x minus f of 0, which is just 0 divided by x, to exist, right? And what is this? This is just x sine of 1 over x divided by x, which is just sine of 1 over x. And obviously sine of 1 over x is kind of undefined at 0, so it doesn't, the limit doesn't exist because it just oscillates. Oscillates up and down.
The people, I think, spotted that it's still got lots of oscillations going on, and the oscillations are going all the way from x to minus x. So kind of, it feels a bit like, it'd be really surprising if someone told me, oh, the derivative of this function is just 3 at the origin. The derivative is just number 3, because it kind of feels like it can't be 3. It's got to be. It looks like it's got to be 1, and it's got to be minus 1. And that's no good. Like, you can't have all of that. It's clearly 1 if you come down the top of the funnel, and it's clearly minus 1 if you come in from underneath the funnel. So yeah, okay.
Yep.
Somewhere in between, no good. Brill. Okay. Was chat more successful on this one than the previous one? Or, yeah, the continuous but not differentiable one. So that's okay. There's a pattern, isn't there? Or maybe I shouldn't say there's a pattern. Okay. Should we do the next one?
Okay. I think people may have seen this one coming.
This is striking me. I should have set this as a curve sketching exercise beforehand. So now we've got sine 1 over x multiplied by x squared. So
I've actually zoomed in the graph quite a bit. This only goes to minus 0.3, which only tells you about what the graph looks like at 0. It doesn't really tell you about what this graph looks like for big X values.
So it's still sine 1 over x is still a very wobbly function, lots of oscillations, but now it's been squashed by a factor of x squared. We've multiplied it by x squared, and that's forced it to lie, I guess, before it was between x and minus x, and now it's between x squared and minus x squared.
Yeah. I mean, for big values of x, this is x squared. For big values of x, 1 over x would be very small. So this can be approximated by 1 over x. So for big values of x, this function should just be like a straight line, right? F of x equals x.
Huh. I hadn't thought about big X.
Which doesn't.
I guess we don't have big X in the picture, and spoiler alert: big X is not relevant to the question of whether this is continuous or differentiable or both. People in chat, so I quite like this mode of I've got the poll on screen, but behind the poll. People are joining in the Q&A, and people have got good suggestions about what's going on. Votes at the moment. Nobody has voted for this to be not continuous. Everyone who's voted so far thinks this is continuous. Aditi, is this function continuous?
It is continuous indeed.
It's really well. So away from 0, super nice. At 0, it's fine. As you get close to 0, the values get really small because of that x squared factor. So the values get really small as you come close to 0. That means that however you approach it, you get close to the value of 0.
Yeah.
It's a good thing you set f of 0 to be 0, isn't it?
Yeah.
You had your choice there, but you picked if you'd sneakily picked 3 or something over there, so that whoop.
Then it suddenly wouldn't be continuous.
Right. And I don't think I'd have noticed, so you'd have caught me out. But yeah, not a trick question. People also think that this one's differentiable at a rate of about 3 to 1. I guess follow-up question is, if you think this is differentiable, what's the derivative at 0?
Yeah, I mean, it does look differentiable, but maybe that's just the way I've plotted the graph because it's very zoomed in. But we can again go back to limit definitions to see. But intuitively, it feels more both continuous and differentiable.
Right. Yeah, and in fact, if you write out... So for this one, I think it is useful to write out the limits. Do you want to...
Yeah. It's definitely neater to see it that way to fully convince someone that this is definitely continuous and differentiable. Okay, so let's do continuity first. So again, it's continuous if the limit as x approaches 0 of f of x exists and equals f of 0, which is 0. Okay, so what is this limit? So the limit as x approaches 0 of f of x is x squared sine of 1 over x. And we can do the usual trick again, that this is less than the modulus of x squared, which does go to 0, because if x goes to 0, then x squared must go to 0. And we do sneakily put these absolute value signs, so we don't have to worry about negative and positive things, because essentially what's happening is that because we've put in this absolute value sign, we have that it's always greater than 0. And we've just proved that it's less than something which goes to 0. So the function between these two values must also be 0.
Yeah, cool. Yeah, no, I love this. So this shows that this is a kind of proof that the squashing factor of x squared is enough to squash this thing to make sure the values get close to 0. Raphael asks a really good question in chat, which is before... Where does it switch over? How many x's did you need? If you put an x to the 1/2 or x to the 1/4 or x to the 3/2? I'm going to leave that as like homework or further reading, I think. It's a good question of, can we play the halfway between game to work out what's going on in between? Is it differentiable? Chat thinks so. Chat thinks that you can differentiate this and I guess get 0 at 0.
Yeah, so let's just go back to the limit again. So limit as x approaches 0 of f of x minus f of 0, which is just 0, over x minus 0, so that's just x. And this is the limit as x approaches 0 of x squared times sine of 1 over x divided by x, so that's x sine of 1 over x. And we did prove that this limit exists and goes to 0 on the previous slide.
Right, so that's x sine 1 over x being nice in the sense that its values do get closer to 0. As you come in. Josh in chat makes a really good point that I hadn't noticed. This is an odd function. F of minus x is equal to minus f of x. It's an odd function, but it's got 0 derivative at the origin. That's a bit weird. And Josh is right, that is a bit weird, but it is true. So there's this kind of, normally when you've got an odd function, its derivative doesn't have to be 0 at the origin. It could be, but it doesn't have to be.
Cubed, I think.
Oh yeah, x cubed. What am I talking about?
X cubed has derivative 0.
What's an odd function says something? So odd function is when f of minus x is equal to minus f of x. An even function is when f of minus x is equal to f of x. So think about x squared or x cubed, the sort of symmetries that you get there. Cool, okay. So we've seen that you can take a function. Chats I think got on board. They've now been getting the right answer is the consensus answer. The first one was horrible. It wasn't continuous or differentiable. The second one was continuous but not differentiable. The third one was continuous and differentiable. There's a missing case. Do you want to say something about that?
So
we've done continuous and differentiable, continuous but not differentiable, and we've done neither.
So is that differentiable but not continuous?
Yeah. Can we do an example that's differentiable but not continuous?
Right. That's a very hard question, because if you think about it, I think differentiability is kind of a stronger statement. It feels stronger. So I think differentiability actually implies continuity at a point. So if a function is differentiable at a point, then it must be continuous at that point as well. Yeah, so you can't have the full.
So it turns out there's a little proof at university maths that if you're differentiable, then you must be continuous if you're a function. So we haven't got an example that's differentiable but not continuous, because that never happens. And that option in the poll was not true for any function. So red herring. Right. Okay. Good. I think we've now got a nice theory about differentiating things, which is sort of not quite the same as how we've been differentiating things before in school, like write down the derivative, right? X cubed, derivative's 3x squared. Move on. Here we've got more of a kind of subtle approach of what do we do if the function's not one of the nice ones that we know the derivative for. Yes, yep. What Anonymous said in chat. True. Cool. Okay. What's next? So we can differentiate. We've got derivatives.
So now we have something called the Fermat's theorem, which has a name apparently. But we studied this in school. You know, we've all come across the fact that, or some of us have come across the fact that the derivative at a turning point or at a maximum or minimum point is 0. And
just for time, sorry, this is behind the scenes chat. Just for time, I think we should skip the proof of this, do Rowley and mean value, and then do fundamental theorem really quickly. Is that right?
Okay. Yeah. Sure. So yeah, hopefully some of you have seen this before. But yeah, the derivative at a maximum point is 0. Let's go to Rowley's theorem, or Rolle's theorem, which says that if you have a function that I'm going to try and draw, and then the function has kind of two particular values, a and b, the value of the function is the same. This is a very bad drawing. The value of the function is the same. So you have something like f of a equals f of b. Then, and if the function is differentiable, which automatically implies that it's continuous. Then we must have a point between a and b, strictly between a and b, such that it's a maximum point or it's a turning point. So the gradient at that point is 0, which hopefully makes sense.
Yeah. So either a maximum like this, where at the top at its maximum value, it's got no derivative, or a minimum point at the bottom. Yeah. And it's got one or the other or both. It's kind of nice. This is true for any differentiable function. It's kind of nice for the picture in there as well. Okay, that's got a name. That's got somebody's name on it. Rowley's theorem.
Rowley's theorem. Okay, and then we have something called the mean value theorem, which is a very important theorem, and it also tells you something about the derivative at a value between two numbers. But then we don't have the condition that the value of the function is the same at these numbers. It somehow seems to be telling us more about, it somehow seems like a stronger statement. So Rowley's theorem actually follows from mean value theorem. So if you have f of b equals f of a, then f prime of x naught is 0. So if you do have that condition, then this does hold. But it feels like it's telling you something extra, that if you have any function, then, so what is this value actually? This is, this is actually the gradient of the line connecting the 2 points. So it's telling you that between A and B, there is a point such that its derivative is equal to the line connecting the 2 points. So hopefully this will be a bit clearer if I show you a picture, which is here.
So here the black line is the function, right? So the black line's got a function, it's going up from f of a to f of b.
So this is a function f of x, and we're claiming that between a and b there exists some x naught, and it may not be unique, as you can see in the diagram. There exists some x naught such that the derivative at x naught is exactly equal to the derivative of the line connecting these 2 points. So f of b minus f of a over b minus a.
Yeah, so it's kind of not obvious, right? That somewhere in between, there's a point that's got exactly the right gradient that matches up the gradient of the overall line segment. An anonymous person says, how do you prove that? We're going to prove this one. We skipped a proof for time, but we're going to prove this one.
Yeah. Okay, so we will prove this one. I do have some, this is kind of the idea. So the idea is to think about making this problem into essentially Rowley's theorem, because we know that Rowley's theorem holds. So it's very similar, but it's not quite. So what we can think about is kind of rotating this graph so that this kind of line actually becomes your x-axis, or you kind of just pull it down about a. So you kind of rotate it about a, so that this function becomes something like this. And try and replicate it. And then you can see that f of a and f of b have the same value. So between them, there must be a point such that the gradient is 0, which corresponds to the gradient being equal to this line, because then this is parallel to the line.
It means something like, I love this idea. So it's like, it's not obvious at all that there's going to be a point that's got the same gradient as the green line, but if you turn your head sideways, then you're looking for a point that's got the kind of same gradient as the green line. And it's kind of more obvious if you turn your head sideways that you kind of want the maximum of that rotated function. Okay, so to prove this, we first obviously need the equation of this line. And then what we are going to do is subtract off. So from each point here, we're going to subtract off this value. So that this line comes down to this f of a value. So that's the plan. And then we're going to try and apply Rowley's theorem to that new function and hopefully get the right answer. Okay, so if we try to work out the equation of this line quickly, this line goes through 2 points. It goes through this point a and f of a, and it goes through the point b and f of b. And we can work out the equation between 2 points. So first, we can work out the gradient. I haven't done this in a long time. A bit of A-level revision for people in A-level.
So the gradient of this line is the change in y, which is f of b minus f of a, over the change in x, which is b minus a. And so the equation of the line is y minus f of a is equal to the gradient.
A-level maths to the rescue. X minus a, right? Yeah.
Minus a. So we've basically done y equals mx plus c, and then substituted the value of m and then x and then c, x and then y. We substituted this point to work out c. So this is this line, and then we're going to subtract it off from the function f of x.
Cool.
This is the function. So we're subtracting off this line from the function, and then we're going to apply Rowley's theorem. So hopefully we should get g of a equals g of b. Right, this is how we've kind of set this up. And let's see. So what's g of a? G of a is f of a, so we're just substituting a into x minus. So a, obviously this thing cancels because it's a, and then you just get f of a minus f of a, which is 0. And g of b is g of b is b minus a, so this becomes b minus a. This cancels, so you get f of b minus f of a, and then there's a negative sign minus f of b plus f of a, which is also 0. So then by Rowley's theorem, there exists a point there exists a point x naught between a and b, such that the derivative of such that g prime of that point is 0. So g prime of x naught is 0. And if you work out g prime of x naught, you get, so g prime of x in general is f prime of x. This is a constant, and this is a constant multiplied by x essentially. So this is just f of x minus f of b minus f of a over b minus a, and this is 0. So then you do get a point such that the gradient of the function is equal to the gradient of the line.
Cool. I kind of like, so the maths on this slide is pretty algebra heavy and do lots of calculations, but the idea of what's going on is just, hey, if we subtract that straight line, then this just turns back into Rowley's theorem that was going on before. Someone says they're lost, but it's fine. You did understand a slide ago. So if you subtract a line, then it's that idea of looking sideways and seeing where the maximum and the minimum is. The actual algebra of doing the subtraction is quite messy, because you've got to write down all of the variables for what the line is, and then actually do the subtraction and put some things in. There was a minus sign outside the big bracket, says Sebastian. People in chat are picking up the pieces of 3 different calculations all at once. I might put a kind of slow motion replay in the further reading. And somebody told me that's GCSE maths to write down the line, but then checking what's going on. Who knows? One thing that's kind of related to my GCSE maths, says somebody who's doing GCSE maths. Cool. Okay, so we've got this mean value theorem, which says the kind of surprising thing that somewhere between A and B, there's a point that's got just the right derivative, just the right gradient to represent the kind of line segment in between. It's kind of nice. Slow-mo replay in the further reading for Maya and everyone else.
Yeah, the mean value theorem is actually very important. You can prove many important theorems from the mean value theorem. I wouldn't say too much about it because you'll learn it in your first year, but the idea is generally just to understand Rowley's theorem. The mean value theorem is equivalent to the Rowley's theorem. It's just rotating the graph. The maths should still be the same if you rotate the graph. If you look at it from a different perspective, it shouldn't change the maths. That's essentially the idea. Okay.
Nice. Rebecca,
so now,
sorry, go. Okay. We got to teach some integration. We got 5 minutes. Yes. We're gonna overrun, but that's all right. We're gonna overrun a little bit because we're gonna teach them integration now. So
right. This looks very confusing, but so what we're saying is that we're dividing. So we have a function between 2 x values a and b. We're dividing the function into some intervals. We're dividing it up into n parts, and then we're calling these x and x1. So this is literally just dividing up the function between a and b into n parts to get kind of like a partition. They don't have to be n equal parts, but they can be. There's nothing stopping them to be. So that is a partition. Okay, and then you can have a Riemann sum adapted to that partition, which again sounds scary, but all it's really doing is calculating the area. So we're kind of introducing integrability as the notion of area under a graph. So we're going to try to obviously make it strict, but essentially what we're doing is approximating the area under a graph. So we're going to divide a and b. So let's say this is a and this is b. We're going to divide it up into some chunks, and then we're just going to work out the areas. And the height of these rectangles can also be pretty general. So in school we generally do things like calculate the area under a graph. We just take the leftmost point and kind of do these rectangles. This is going to make it probably more confusing, but we do these rectangles. But actually, the kind of representative you choose for each partition can be any point. So you can kind of just choose this point x, maybe not x, v1, to represent the height of this rectangle. And this is what the sum is doing. It's just summing up. It's multiplying it's just doing the area of a rectangle and then adding them all up. So it's multiplying the width times the height. The height is going to be the value of the function at that point. So it's just some point between your 2 partition points, and then you work out the value of the function at that point, which is the height of the rectangle, and you multiply it by the width. and then you add them all up, and that should give you an approximation for the area.
It's a yeah. So Ali in chat says it's a bit like the trapezium rule, and I think that's right. Except it's kind of worse than the trapezium rule, because instead of cleverly using trapeziums, it uses rectangles, and the rectangles have their heights chosen at just some random points in between. So the partition is kind of the formal word for chopping it up horizontally, and then the Riemann sum says take some rectangles, pick the height to be, I don't know, something in that region, choose some value in between uj in between, and just set the heights kind of almost at random to some points in between. Those blobs on the curve are just somewhere in each region, and that gives you a kind of approximation to what the area under the curve is.
Yeah,
so that's nice.
So this is just approximating the area, I guess. That's exactly what it's doing. And then we can define what it means for a function to be integrable. So again, this looks confusing. But what we're saying is that if you have a function and if you have some partitions, now you can actually have a sequence of partitions. So you can kind of refine these partitions or to make them more and more accurate. Or so you kind of have a function, and then you maybe do some partition. You partition it into maybe 5 different rectangles, and then you can work out the area using that. Or you can do this again and again, and you can maybe use more partitions here, more intervals here, and then you can do that again and again. So, and then obviously you have to make a choice for the value of the points in each section. And what we're saying, if a function is integrable if no matter how you choose these points and no matter how you choose these partitions, if the limit of these areas go to the same number, then the function is integrable.
Okay, so yeah, so this means that it's sort of the definition of how we chose those rectangles has some kind of randomness in it, or just you chop the horizontal axis up a bit and then pick some values in between, and somehow that shouldn't matter. None of that should matter. There should just be some sort of if however you do that, you get the same answer when you chop it finer and finer and go finer and finer rectangles. If you always get the same answer, that's good. Then you're integrable. So we've got this kind of freedom of how you pick the rectangles in our definition, but then it sort of shouldn't matter. If it doesn't matter, then the function is called integrable.
It is integrable. Exactly.
Cool. That's the definition.
And also you have kind of this reverse implication that if a function is integrable, so given a function is integrable, we can say something about the limit of the partitions. So then the limit of these partitions is the integral.
Sure.
So
okay. In fact, it's like the area under the curve. So that's nice.
Yeah.
Cool.
Okay. Then you have a function, and then you can see if it's integrable or not. So this is kind of this is not continuous anywhere because it kind of just bounces up and down between 1 and 0. So is this function integrable? So it's 1 on the rationals and 0 on the irrationals. The graph kind of just looks like a line through 1 and 0 because there are many rationals and there are many irrationals.
I'm not going to turn the Slido poll on. I'm going to leave them to think about this one.
Okay.
And also because earlier people were a little bit worried about that function where you did it piecewise and you just had a value. This one's much weirder, right? Still a function because you've decided what the value is for all of these. It's super crazy. It's 1 at all the rational values and 0 if x is irrational. Can you stick some rectangles on that? And if you do, when you stick your rectangles on it, do you get a sensible answer for what the integral is? Gonna leave that one for chat to think about.
I mean, this is a well-defined function because every number between, I guess, -4 and 4 is either rational or irrational. So every number does get a value. So it is a well-defined function.
That's a really weird function, though.
I agree.
Okay. Cool.
No, it's not. Okay. So now we have the fundamental theorem of calculus. So this is what we want to prove. This may seem simple, you may have seen this before, but we can actually prove this. It's not an obvious fact at all. Integration and differentiation are completely introduced in a completely different way. So it's not obvious that they should be related in this way, that the derivative of a function is related to the value of the function. Okay, so we can try and prove this now.
I love this result. So this says if you can differentiate, then you can integrate to get back to your original function.
Yeah, exactly. let's go to the proof. So the proof basically relies on the mean value theorem. The mean value theorem is the key idea. This is why we had to kind of cover all that theory. So if you take any partition, then what we're saying is that there is a choice of these. This is why we were so general about the choice of the numbers between the partitions. The idea is that there is a choice of these numbers between these values xj minus 1 and xj, such that we can make this area to be what we want, such that we can make the area under the curve what we want. So I think a diagram would help. So if you have a function, and then if you divide it up into some partitions, let's do 4 partitions. So what we're saying is that we can choose these numbers, u1, u2, u3, and u4. Between these other numbers, it gets messy, such that if you represent the rectangle, the length of that rectangle by the function value at u1, and then if you add these areas, then the total area would be f of b minus f of a. And you can do this for any partition, so that if you have a sequence of partition, then the limits must tend to this, because the value of the area of any partition is f of b minus f of a. This can seem very confusing at first, but
so this is sort of brilliant. So we've overrun a little bit, but it's worth it for the kind of brilliance of this proof. The definition of integrable has this kind of freedom of choice that it shouldn't matter how you choose the rectangles or how you choose the points inside. So here's a very precise way. Don't choose them at random. Choose the points very precisely with the mean value theorem, so that each little contribution to the integral, each little contribution to that sum, I suppose, each little contribution is exactly what you want it to be. So they all add up to, hey, well, if it doesn't matter, then I can choose exactly, very craftily, choose how I want to put points in. And then things simplify nicely down to f of b minus f of a, which is just lovely. It's sort of a clear relationship between the sort of differentiation that we had before and the sort of integration that has just been defined. So that even though this thing looks a little bit weird because of the partitions and the choice of values in between, it's sort of related by being the inverse of differentiation. Very cool. Yep. Thank you. Thanks for showing us the fundamental theorem of calculus. Integration and differentiation are linked together like that. Cool. Just time for Molly's fun fact of the week. Molly's fun maths fact of the week is that there is such a thing as the Mental Calculation World Cup, with rounds including calendars, square roots, and the challenge event, as if the others weren't challenging enough already. The next event is in autumn 2021 in Germany, so get ready to do some mental calculations. Thank you, Molly, for the fact of the week. Maya says, I'm usually fine in the first 50 minutes, and then the last 10 minutes are different, which is, I think, what we're going for on this show.
If it makes it any better, I struggled with this content a lot last week because we were learning it last week, so it is hard.
Me too, but not last week when I saw this as well. It's worth it for getting a kind of cool understanding. If you understand this, then you end up understanding integration and differentiation and how they're actually linked together for a huge variety of functions. Okay, I'm going to wrap up the live stream there. I'm going to hang out and chat a little bit. I saw some good questions that I haven't answered, so I'm going to hang out and chat for a little bit off stream. Thank you very much for coming on the live stream. Anything you want to say to wrap up? Anything we should have said that we haven't said?
No, I've really enjoyed doing the live stream. Thank you, everyone.
It's been great to have you on and do some tricky university maths. If you want an idea of what's going on in Aditi's life at the moment, you've got exams coming up quite soon. So
I do have exams coming up quite soon, yes.
This stuff's, I guess, on your mind at the moment. learning how everything's related together. Right, okay, people are saying thank you in chat. We're going to wrap up there. We'll see you in 167 hours for another episode of the Oxford Online Maths Club. Stay safe, and I'll see you next week. Bye.